Hi, my name is Travis Thompson. I'm with the research group at Biosynthetic Technologies. Today we'll be looking at an oxidative stability review of estolides. To take a look at what the agenda looks like for today, first we're going to take a look at an introduction to estolides and the estolide chemistry. Next we'll do a review of oxidation and antioxidant mechanisms. It's just a quick overview of that. Third, we'll take a look at some antioxidant optimization studies as they relate to estolides. We'll then go into a base oil oxidative stability comparison of different products, followed by a method review where we compare RPVOT results to RSSOT results to compare the two to one another to see how they're similar and dissimilar. And finally, we'll take a look at the formulation advantages of estolides in an ISO VG68 formulation, and see how swapping out certain base oils in that formula with estolides affected the oxidative stability. So first, just kind of a quick introduction to estolides. Estolides are oligomers of fatty acids. They're a class of synthetic base oils. They have several advantages actually over traditional products. They have high oxidative stability, high hydrolytic stability, and also good environmental characteristics such as biodegradability, low toxicity, as well as low potential for bioaccumulation. These products, because they're synthetic in nature, they can really be custom tailored to meet the needs of just about any application. Properties such as pour point, viscosity, polarity, and many others can be optimized, can be adjusted. If you look down below, you can see the different functionalities, functional groups that can be modified in the synthetic process. So there's the alpha group, which sits on top of the top fatty acid chain there. That can be modified. In the middle, the fatty acid length can be modified. It can be shorter, it can be longer, it can be branched. The length of the oligomer can be modified. Short oligomers allow for low viscosities. Long oligomers allow for high viscosities. There's also the beta group there in the bottom right-hand corner. The beta group can also be modified. So that's typically you're esterified there with an alcohol. Different alcohols can be used to enhance hydrolytic stability, enhance viscosity, change other characteristics. You can also esterify with glycols and other components as well. So there's a number of different angles here and ways we can manipulate the estolide chemistry to make sure that they fit the needs of the application that they're being used in. So I'd like to give a quick overview on oxidation. So how does oxidation occur in a lubricating system? So the first thing that needs to happen is initiation. Initiation is where the first free radical is formed. This right here, this R dot here, that's the radical that's been formed. So in order for this reaction to proceed, what has to happen is there needs to be high temperature, there needs to be either light or some kind of catalyst. The catalyst present could be some sort of acidic component present in the base oil, in the lubricant formulation, or it could even be something like an oxidized metal surface, or just the elemental form of the metal surface could be contributing as a catalyst in the system. Either way, if initiation proceeds, you get this free radical. Free radicals are extremely reactive. So once a free radical is formed, this cascade of secondary reactions is going to occur. So the free radical will form. After initiation, you have propagation where peroxides are formed. Those hydroperoxides react with other components and eventually go on to the branching step. The branching step occurs, alcohols are formed, water's formed, more free radicals are formed. And then in the termination step, termination is where multiple free radical components, whether they're created through initiation or propagation or branching, combine with one another to kind of neutralize the radical and form some kind of final byproduct where this kind of this chain reaction ends. Now, termination products can cause increases in fluid viscosity, formation of sludge, increases in acidity, and further accelerate future oxidation. The components that are formed in termination, for example, acids that can be formed in termination, those acids can be cause for further catalysis of oxidation itself. And so in this way, because oxidation products allow for more rapid oxidation, you get sort of an exponential increase in oxidation over time. If the process is interrupted, however, prior to termination, then the process can be drastically slowed. The additives that are used to interrupt this process are referred to as antioxidants, and that's what we're going to be talking about next. So types of antioxidants. There's three primary types of antioxidants. There's the primary, there's secondary, and there's tertiary. Primary antioxidants remove peroxide radicals from the oxidation process. So you can see here in the propagation step, this peroxide, if it's removed from the oxidation process, then the product of that propagation step cannot be generated. And so if those products aren't generated, then branching can occur and termination can occur. So in this way, you've kind of eliminated or you've slowed the oxidation process. Similarly, the secondary antioxidants function by decomposing hydroperoxides. So hydroperoxides are the reagent in the branching step right here. Again, if those are removed, then the cascade that occurs after this step will not occur. And again, you won't get those termination byproducts that kind of disrupt your lubricant. The final one here is the tertiary antioxidants. Tertiary antioxidants serve by removing the catalyst from the oxidation process. So up here you can see for this initiation step, you need some sort of catalyst to be present in the fluid. The catalyst can be something like an acid, it can be something like an oxidation product of a metal surface, it can be just an elemental form of the metal surface. So typically these tertiary antioxidants, what they do is they inhibit the formation of catalyst species by serving as metal deactivators. And so they'll neutralize the surfaces of metals so that those metals can't act as catalysts in oxidation. By removing the catalyst, you're going to get less of this initiation occurring, less free radicals, and thereby less overall oxidation of the system. Antioxidant selection. So for the purposes of this initial evaluation, what we looked at was only primary antioxidants. So we looked at aminic and phenolic chemistries. Aminic additives are typically recommended for applications with higher temperatures, so greater than 120 C. Phenolic additives are usually recommended for systems that are less than 120 C. Typical treat rates for these types of additives, primary antioxidants, range anywhere from 0.1% to 2% depending on the base oil, the additive, and of course the application you're going to be using these in. And then finally here, one note to kind of keep in mind is that aminic and phenolic chemistries are known to yield synergistic effects with respect to antioxidant, with respect to the AO effects. So a combination of these additives was also investigated as part of this study. So here's a look at some of our antioxidant optimization work. First, what we did is we took a low viscosity estolide and we screened different antioxidants. There were three types of antioxidants we tested. We tested aminic antioxidants, which are the first three columns here in this graph. The second three columns here are the phenolic additive that we tested. And then in the final column here, we looked at the 50-50 blend of aminic and phenolic chemistries. The aminic additive that we looked at was non-elated diphenylamine. Non-elated diphenylamine is a liquid aminic antioxidant that's very commonly used. The phenolic additive that we used was 2,6-tert-butylphenol. And then the 50-50 blend was just a blend of these two components that was tested. In each of these three sets here, the first column that's very, very low represents what the low viscosity estolide looks like without any additives at all. The second column is with 0.5% additive, and the third column is with 1% additive. So you can see aminic performed better than phenolic on its own, but the 50-50 blend of aminic and phenolic performed better than either aminic or phenolic at their respective concentrations. So it was determined that a blend of these components was going to be more effective moving forward. And so most of our other experiments from this point on were done using a combination of aminic and phenolic additives. Next, we took a look at an AO optimization on treat rate. So we wanted to understand what treat rate is most effective for a 50-50 blend of aminic and phenolic additives. So what we did was we tested a range. We first blended the aminic and phenolic antioxidants at a 1-to-1 ratio. And then we took a look at these additives as part of a formulation ranging from 0% to 2% over on the right-hand side. And what we found was the most effective range, at least as it showed on the RPVOT test, was between 0.75 and 1.25%. These results here are actually really close to one another. 1,423 minutes, 1,464, 1,460. So really anywhere in this range is effective. We decided to move forward with 1%. So 1% is typically what we use now in our formulations. Next, we wanted to understand, is there some sort of optimal ratio of aminic to phenolic additive in the formulation? We know that having an aminic additive and a phenolic additive in the formula yields this synergistic AO effect, but what ratio of those two components actually provides the most benefit? And so that's what we did here. In the top here, we started with 0%. The first number represents how much aminic additive is in there. The second number represents how much phenolic additive is in there. Again, they were all added at a 1% net treat, but of the 1%, this is the ratio of aminic to phenolic that was present in that 1%. So this top one here is all phenolic. The one at the bottom is all aminic, and then in between shows varying levels of aminic and phenolic that are included as part of that 1% treat. What we found was the most effective ratio tested was the 90-10 ratio. So 90% aminic, 10% phenolic, though the 50-50 looked good as well. So anything really either 50-50, 70-30, or 90-10 of the aminic phenolic, using an aminic phenolic ratio of any of those, yielded about the same results on the RPVOT test. They were all just about 1,400 minutes, or between 1,300 and 1,400 minutes. Base oil comparisons. Excuse me. So next, we took a look at different base oils treated with this 1% antioxidant. So again, we're using the 50-50 blend of aminic phenolic. We're treating these base oils with 1% of that additive blend, and we're comparing estolides to a number of other base stocks. The chart in the bottom left-hand corner is low viscosity. The one in the top right-hand corner is high viscosity. So let's start with the low viscosity chart. You can see estolides are the column all the way to the left. So the first column at about 1,300 minutes. Next, you can see vegetable oil, which was a high oleic canola, which is pretty low, but makes sense considering they have the unsaturates present in the vegetable oil. Then we have group 2, group 3, low vis PAO, low vis PAG, TMP trioleate, again, which was relatively low, and that's because this is an unsaturated ester. The second to last here is diethyl hexyl sebacate, and the final one is a polyol ester. These are all low viscosity products, and as you can see, the Estolide product was really comparable to the other high quality base stocks, group 3, PAO, the saturated ester diethyl hexyl sebacate. So the Estolide product performed very well. On the right hand side here in the chart in the top right, this is the high viscosity comparison. The first column in that chart is the mid viscosity Estolide, and the second column is the high viscosity Estolide. You can see that these two products really drastically outperformed the other products that were tested. They were better than PAO, PAG, the complex ester that we tested. Really nothing got close to our products here. So they seem to be superior to these, at least using this particular additive system and concentration. So method comparisons, taking a look at RPVOT as it compares to RSSOT. So these are two oxidation tests. The RPVOT test is probably kind of the juggernaut of oxidation testing in the lubricant industry. It's the most common test method that's used to characterize relative oxidation times of lubricants. We don't have access to an RPVOT analyzer in the lab. We have an RSSOT analyzer. So we were curious to take a look at RPVOT, compare the results of that to what we're getting on RSSOT in the lab, and then see if there's any conclusions we can draw related to, is there a correlation between the methods? How are the methods similar? How are the methods different? So we just wanted to do kind of a deep dive into these two pieces of equipment. So here's a comparison of the two methods. RPVOT is ASTM D2272. RSSOT is ASTM D7545. Obviously, RPVOT is run on an RPVOT test apparatus. What we have in our lab for our SSOT is an Anton Par Rapidoxy 100 unit. The volume of sample needed for RPVOT is 50 milliliters per run. For our SSOT, you only need 5 milliliters. So this is one significant difference between the two methods. You only need about 10% the volume of sample to run our SSOT as compared to RPVOT. The temperatures are about the same, 150 C for RPVOT, 140 C for our SSOT. Again, also the pressure of oxygen is about the same as well, 90 psi for RPVOT, 100 psi approximately for our SSOT. The end of the test, how you define the end of the test is a little bit different between RPVOT and RSSOT. For RPVOT, end of test is when the oxygen pressure inside the vessel has dropped by 25.4 psi. Now that's about a 28% drop in pressure. For RSSOT, the end of the test is defined when there's a 10 psi drop, which is about a 10% change in pressure inside the unit. Test time. So for durations, RPVOT can run for as long as 2,000 minutes or even longer in certain circumstances. Our SSOT, typical values, high values on our SSOT are around 500 minutes. So there are shorter test durations. You're looking at approximately 25% the time to run our SSOT as compared to RPVOT. So correlation data. So what we did was we took 4 samples and ran them on RPVOT and on our SSOT. We looked at a low-vis estolide, a low-vis PAO, a high-vis PAO, and a complex ester. We had the RPVOT data already, so we took those. We also ran them on this RSSOT instrument. Now, if you plot on the y-axis RSSOT and on the x-axis RPVOT, you'll get a chart. You'll get the chart there in the bottom right-hand corner. You can see there is a linear correlation between the data points with an R-squared value of 0.827, which is a decent linear correlation. I mean, it does appear that the lowest value on our PVOT, which is the complex ester, was also the lowest value on our SSOT method. Similarly, the highest value here was the low-vis PAO on our PVOT. That was also the highest value on our SSOT method. So it does seem that there's a general correlation here, though really there's going to have to be more data generated to really verify the robustness of this correlation and whether or not we can truly swap out long-term our SSOT for our PVOT. Next, we'll take a look at some formulation advantages of estolides and how they can benefit formulators in terms of oxidative stability. Now, we're going to show you just one example here. In this example, there's 3 formulations. So the starting formulation 1, was a formulation that contained no estolide. It had 25% complex ester, 74% PaO6, and 1% of an eco-label hydraulic fluid additive package. What we did was we took that formulation and we took the complex ester out. In place of the complex ester in formulation 2, we put a high-vis estolide in there at approximately the same concentration, so 25%. What we saw was the RPVOT went from an initial value of 980 minutes to now a new value of 1,214, which is something like 25% gain in oxidative stability per the RPVOT test. In formulation 3, similarly, we took out the complex ester, we took out about 30% of the PAO6, and we substituted those for a mid-viscosity estolide. In this case, formulation 3, the RPVOT jumped to 1,328 minutes from a starting point of 980 minutes. This is a gain of something like about 35%, which is substantial. Now, keep in mind, all 3 of these formulations are an ISO 68 formula. So we held the viscosity constant, and we just looked at changing the ratios of the base oils, changing the types of the base oils, and these are the results we got. So this is pretty neat data showing that the stability of estolides can really be leveraged by formulators to improve the oxidative stability performance of their products. So just a few comments now in closing. Conclusions and some future studies. Number 1, aminic and phenolic AO chemistries are effective with estolides. A combination of these two yields a synergistic effect. Number 2, optimal treat rates of the 50-50 aminic phenolic blend is between 0.75% and 1.25%. The optimal ratio of aminic to phenolic in a formulation is 90-10, though this ratio can be adjusted to as low as 50-50 without much of an effect. Low viscosity estolides have oxidative stability on par with top base oil performers. This includes group 3, PAO, and saturated synthetic esters. Though the high and mid viscosity estolides do seem to have stability that's higher than similar high-vis synthetics, including PAOs and PAGs, which is fairly interesting. The RSSOT results showed a correlation to RPVOT, but we really just have limited data at this point. We have 4 data points, so more data is really needed to understand the strength of this trend. Exchanging a complex ester with estolides in an ISO VG68 formulation did yield oxidative stability gains of between 25 and 35%, which is also substantial. In terms of future work, what I'd really like to do is evaluate secondary and tertiary antioxidants in addition to what we evaluated here, which was mainly the primary antioxidant type. And number 2, I'd like to do further testing to evaluate the robustness of this correlation between RPVOT and RSSOT. With that, I want to thank everybody for attending my presentation today. If you guys have any questions, feel free to reach out to me personally. My email is on the first slide of this presentation, and I'm sure you can find it on file with STLE. But you can reach out to anyone at Biosynthetic Technologies, and we'd be happy to help you out and answer any questions you have. Thanks everyone for your time, and thanks for listening. Bye-bye.